Welcome back, everybody. In this video, we're starting section 4.5, which is about logarithmic properties. As we saw, the logarithm functions are inverses of the exponential functions. As you know, there's a bunch of different exponent rules you have to know. Since the logarithm functions are inverses of the exponential functions, it makes sense that there's a few properties or rules for logarithms. And this section is where we study those. Okay, so the first thing I wanted to do is review some logarithm properties that we have already seen. And so the first one is that the bases here are all a, okay? The base a logarithm of 1 is equal to 0 because a raised to the 0 power is 1. The base a logarithm of a is equal to 1 since a to the first power equals a. And then the next two properties come from the fact that the logs and exponentials are inverses of each other. If you compose the two, you just get the identity function. That is, if you take a to the x power, and then take the logarithm of that, you're back to where you started. Similarly, if you take the logarithm of some number and then raise your base to that power, then you're going to be, again, back to where you started. One other thing I wanted to point out is, because it looks slightly differently with the natural logarithm, remember the natural logarithm has abbreviation ln. So if you see ln e, that's going to equal 1 in the second property. All right, so those are properties that we have actually seen before. So I want to go on to some that are new next. There's 3 in this section that we'll want to know. And the first one is the product rule. So the product rule for logarithms says basically, if you have a logarithm of a product, then you can replace that by the sum of the logarithms of the two factors. So it turns a logarithm of a multiplication into a sum of two logarithms. So it changes multiplication into addition, essentially. So this reads, this one, our book has stated this with b for the base, and that's fine. It says the base b logarithm of m times n will turn into the base b logarithm of m plus the base b logarithm of n, and that's for, of course, any bases bigger than 0. What this reminds me of, we're not going to go through proving these rules, but what this reminds me of is the exponent rule that says if you have 2 of the same base raised to powers and you're multiplying, then you end up adding the exponents. So in a way that relates a multiplication to an addition of exponents. And so that's basically kind of what this does. We're taking the log of a product, a multiplication, and it turns into an addition of the logarithms. So just a couple of examples how we could use this property. So here we have the base 3 logarithm of 30. So I could write the inside as 3 times 10 if you want. And so now we can rewrite that as the base 3 logarithm of 3 plus the base 3 logarithm of 10. So the logarithm of 3 times 10 turned into logarithm 3 plus logarithm 10. And then, of course, we could simplify the base 3 logarithm of 3. That's 1. So we'll have 1 plus the base 3 logarithm of 10. Okay. We have 2 more. The common logarithm of 400, I would look at that as the common logarithm of 4 times 100. Of course, you could look at this as 8 times 25 or, a whole bunch of different ways of factoring it. But I know that this is the base 10 logarithm, and I know that 100 is 10 squared. So that's why I'm factoring power of 10 out of that. So this will be a logarithm of 4 plus the logarithm of 100. Okay, the logarithm of 4, I don't know how to simplify that, so we're going to leave it. Yeah, but the logarithm of 100, that's 2. Okay, if you want to be real clear that that's the logarithm of 4 plus 2, not the logarithm of 4 plus 2, then you can wrap that part inside of parentheses, the logarithm of 4 part. Okay, so next up we have the logarithm of 5 plus the logarithm of 6w plus the logarithm of k. So I'm going to use this property twice, one time to combine the first 2 terms. So this, for one thing also, we're going the other direction with it. Instead of splitting up a logarithm into a sum of logarithms, we can go the other way with it and combine logarithms. So this will be the logarithm of 5 times 6w plus the logarithm of k. Okay, we'll do that again. So then 5 times 6, obviously 30, that's 30w. So we'll have logarithm 30wk. And then probably people want to put that in alphabetical order, and that's a nice idea. So let's go ahead and do that. So let's say log 30kw. All right, so this rule says that if you have a logarithm of something times something, a product, then you can turn that into the sum of two logarithms, and that's the product rule. Okay, we have a quotient rule for logarithms next. This is the second out of the two rules. We have a quotient rule for logarithms, and this one says if you have the logarithm of a quotient, surprise, surprise, if you have the logarithm of a quotient, then you can turn that into a difference of two logs. So base b logarithm of m divided by n, and that will be the base b logarithm of m minus the base b logarithm of n. Here they forgot the line from the fraction bar. All right, so this one I think is kind of neat. The whole thing is kind of neat because multiplication and addition are kind of related to each other, and division and subtraction are kind of related to each other. And again, this reminds me of this exponent rule. If you are dividing and you have two powers of the same base, then you end up subtracting exponents, right? Like if you had x to the 12th power divided by x to the 7th power, you would simplify that to be x to the 5th power, right, by subtracting exponents. So that's what we'll do here. So I'm going to take the logarithm of 1/100th. That's a quotient, a log of a quotient. So I'll write it as a difference of two logs. That's log 1 minus log 100. Okay, and both of those I can actually simplify. The logarithm of 1, 0. The logarithm of 100, 2. So that's just -2. Okay. In the next one, I actually can use both the product and quotient rule. This is the logarithm of a quotient. So I'm going to write that first as log AB minus log C. And then we're going to split that up even further. The log of AB, we'll rewrite that as the log of A plus the log of B. And then don't forget that log C in the back. Okay, so that does that one. The next one's got natural logarithms in it, and that's fine. It's going to work the same way. This one, we have it already as a difference of two logarithms. So we can rewrite that as the logarithm of a quotient. So this will be the natural log of 27 over t. All right, so in these, we've seen some examples where we started off with one logarithm and then we split it up into a bunch of logarithms, or we started off with a bunch of logarithms and we kind of combined them all. And so the question comes up, well, how do you know which one do you want? Do you want to take like this log 27 minus log t and combine it all? Or is it better to take the single logarithm of AB over C and stretch it all out? It depends on what it is that you're trying to do, okay? Basically, are you trying to solve an equation, or are you trying to graph something? Like I said, it depends on what you're trying to do. It's kind of like saying, well, x plus 7 squared is equal to x squared plus 14x plus 49. Which one's better? Well, again, it depends on what it is that you're trying to do, right? So some people would argue that this one with a 49 in it, it's simpler because there's no parentheses. But if this is in the denominator of a fraction and I'm trying to figure out where the vertical asymptote is, then factored is going to be better, right? So it just depends on what you're trying to use it for. So wording that tells you what to do, okay? This last one, this would be combine, might be the direction word, or write as a single logarithm. Awkward silence, sorry. And then if it starts off as a single logarithm and we want to expand it, the wording might be expand. or write as a sum or difference of logarithms? Okay, so we could write that as expand or write as a sum or difference of logarithms if we wanted as a whole bunch of individual logs. One thing that is important to note is that if you are going to do this, you need to go all the way with it. Like right here for the log AB minus log C1, that would be like partial credit. It's not all the way done. When you're trying to expand a expression with logarithms, you want to break it up as far as you possibly can. And if you're trying to combine a expression with logs, then you don't want to kind of do it halfway either. You want to combine it just into a single logarithm. All right, so before we go any further, I wanted to point out a couple of non-properties. So far, we've seen that you can turn a log of a product into a sum of logs, or you can turn a log of a quotient into a difference of logs. Some things that people try that are just not true. The log of a sum isn't anything. There's no rule about the log of a sum, okay? It's especially not the sum of two logs. People look at this and think they're kind of like distributing the log symbol, and it just doesn't work that way. It's not true. Similarly, if you have the log of a quotient, you can't just take the log of the top and the log of the bottom. Okay, those are also just not true. Okay. As you're just starting out, it might be a good idea just to write down the properties that are true on a piece of paper and keep it next to you while you're doing your assignments, so that you don't assume things to be true that are not true. Okay, all right, our last property is going to be this one. It says the power rule for logarithms. And it says that if you have a log of a power, no shock there, the base b log of m raised to the n power, you can bring that exponent in around front as a multiplier. So you have n times the base b logarithm of m. So this turns a logarithm of a power into a product. So it relates powers and products. And so what it reminds me of is this exponent rule, p raised to the r power raised to the s power. When you're raising a power to a power, which is power, you end up multiplying the exponent. So it kind of relates powers and exponents. That's what this logarithm rule reminds me of. So some examples. So 7 logarithm of x, that is the same as logarithm of x to the 7th power. Okay, for logarithm of the square root of 36, I'm going to do this in 2 ways. One, the square root of 36 is just 6, so this is the same as logarithm of 6. And then let me actually do this one on the calculator so that you can see what it is. So the logarithm of 6, I'll turn the calculator on first, is about 0.7781. Okay, remember that the square root can also be thought of as raising a number to a 1/2 power. So we'll say log square root 36 is the same as log 36 to the 1/2 power. And now finally, we're going to use our product rule. That log of 36 to the 1/2, I'm going to bring the 1/2 around front as a multiplier. So that'll be 1/2 of log 36. So now I'm going to type that into the calculator. So we'll have log 36, that's about 1.556, let's say. And so that is about 0.778. All right, so it's pretty close. I've dropped off some digits there, but it should be clear that those are the same. Okay, so next example, we have the natural log of x squared y cubed. So this one is fun because we get to use 2 properties. I have a single logarithm, we want to expand that. So it's a product. So the first thing I'm going to do is rewrite that as a sum of 2 logarithms. I can't just bring the 2 around front right now. Or I'm not going to. So I'm going to rewrite this as log x squared. Actually, I cannot. Log of x squared plus log of y cubed. Okay. And then that's log of a product turned into a sum of 2 logs. That was the natural log. I should better use the correct symbol for that. Okay, so natural log x squared plus natural log y cubed. Now we'll use that power property to bring the 2 and 3 around front as multipliers. So we have 2 natural log x plus 3 natural log y. Okay, so that is our power property. Okay, so a couple more examples. In these next examples, we'll be using just any of the 3 properties as we see fit. So the directions here are to write as a single logarithm. So here we have a sum of 2 logs, but I can't just use the sum rule for this because of the coefficient of 2. So the first thing I'll need to do is use the power rule to bring that 2 inside as an exponent. So we'll have log base 3x plus log base 3y squared. Okay, so then we have a sum of 2 logarithms. We can rewrite that as a single logarithm of a product. So this will be log base 3 of x, y squared. Okay. So for this next one, you should try it yourself. Pause the video, try it, see what you get, and then restart the video and see if it checks out. All right, so we've got a sum of 2 terms, and then in the back we have minus 2 times this other thing. So we're going to do this in a couple of steps. So for the first 2 terms, I see a natural log 5 and a 3 natural log x. So I'm going to combine those. But before I do that, I'm going to bring the 3 inside as an exponent. Remember, for our product rule, there was nothing in front of the log symbol. So I need to do something about this 3 that appears here first. So we'll call that natural log 5 plus natural log x cubed. And you know what? I probably need to get rid of this negative 2, or this 2 also. So we'll keep the minus, and we'll call that natural log x squared plus 5 squared. Okay. All right, so now for the first 2 terms, we can combine those into a single log of a product. So we'll have natural log 5x cubed, and then we'll have minus natural log x squared plus 5 squared. And then finally, this is a difference of 2 logs. So we'll rewrite that as a single logarithm of a quotient. So we'll have natural log of 5x cubed divided by x squared plus 5 squared. You could multiply out this denominator, but there's no real benefit in doing so. So you probably just want to leave it like that. So we started off with a string of individual logarithms, and we applied our log properties to combine all those. All right, so we do have more examples to come, but that takes us to the end of this first video. Let me know if you have any questions, and have a great day.